So I'm going to be talking about compaction and quenching in high redshift galaxies. And I'm hoping that this will be a nice complement to Guillermo's talk, because I'm going to be talking about the theoretical side of these issues, which we just started discussing here during the discussion session. So because Guillermo gave that really nice introduction to the observational side of things, I won't dwell on this too much, but let me remind you that we've known for quite some time now that star formation and the inner structure of galaxies seem to be intimately tied. So this is work that was done here at UCSC by Edmund Chang. And what you see here is color as a function of Sirsic index. I should say these are stars in galaxies at intermediate redshift of about 0.5 to 0.8 from the deep survey. So if you plot the Sirsic index versus color, what you see is that there's all these outliers here that Edmund has color-coded. But then if you plot the same sample as a function of sigma, so the stellar mass surface density, you see that they form this very nice tight correlation. And this is very suggestive of the fact that quenching might be tied very closely to the structure of the inner structure of galaxies. And as Guillermo was just showing, there's these very compact quenched galaxies that we see at high redshift. And what he was able to do in his nice work with the candles data is show that the progenitors of those red nuggets are most likely these very compact star-forming blue nuggets. And what I'd like to address in this talk are what I consider to be three important open questions. The first is, what drives the compaction of these galaxies? What quenches them? And then, what is the exact evolutionary path from being diffuse and star-forming to quenching? So the simulation sample that I'm going to be using here is HydroArt. And the reason why you've heard both myself and Nir and Shigeki and on Monday Kenza discuss this sample is because it's a relatively large sample for such a high resolution simulation. So we have 30 galaxies that are very high resolution. Their feedback prescription is thermal feedback from supernova plus radiative pressure. And in these simulations, tau IR is set to 0. And these are the generation 3 simulations that I think Daniel will be telling us more about on Friday. So we're talking about the centralmost regions of galaxies, right? The central 1 kiloparsec about. So the most natural connection is stellar bulges. So if you look at the 30 galaxies in our sample, and you ask, where did the stars that live in the bulges of these galaxies form? So you take all the galaxies, you stack them and average them, and you look at it as a function of redshift. And what you see is, if a star formed in the bulge and currently lives in the bulge, it contributes to these blue histograms right here. Now, if it formed in the disk and migrated into the bulge, it contributes to the green histograms. And if it formed in a secondary galaxy and was accreted during a merger, you see it in red. So the startling thing that we found was that nearly 60%, or more than 60% of the stars in bulges at redshift 4 formed there. So there's a lot of in situ star formation. And this is true even at redshift 1, where the relative fraction is decreased to 40, but that's still a lot of in situ star formation. And this tells you that there's a lot of wet inflow. There's a lot of dissipative processes taking place here. And there's obviously two obvious ways you can bring in all this gas to the central regions of these galaxies. And one is from wet mergers, and the other is from disk instability. And so what happens is when you have a highly perturbed disk, which has these extended transient features and giant clumps, is that, you have perturbations which drive out the angular momentum, and that brings mass inflow in. And in a paper with Avishai last year, we found that you can basically estimate it as approximately 25 solar masses per year of gas inflow to the central regions of these galaxies at about redshift of 2. So there's all this gas coming into the central regions of these galaxies, which fuels in situ star formation. So what does this mean for blue nuggets and red nuggets? So this is a movie similar to Lauren Porter's work. But this is not with the semi-analytics. This is with the fully hydro simulations. And what you'll see as this evolves in time is that galaxies go from being star-forming and diffuse up to being compact and quenched. And because it's a little bit hard to see exactly what's happening in the movie, let me just zoom in and say that at high redshift, between redshift 6 and 3 in these simulations, what we see is this population which resembles what Guillermo just showed, compact, star-forming blue nuggets, if you will. And then at lower redshifts of between 2 and 1, we see that these galaxies are starting to quench and form red nuggets similar to what we see in observations. Yeah, please. That answers it? Okay, so it's very hard to see what was happening in those movies, right? So let's look at individual cases. So these are 3 galaxies. They're pretty representative of the galaxies in our simulation, which become blue nuggets. And what you see is that they evolve in this direction first, so they compactify, and then they quench. So there's obviously a lot of physics going on here, and we want to investigate that in detail. So I'm going to be showing a figure here that looks rather complicated, so let me take some time to explain it. This is the mass within 1 kiloparsec of a single galaxy, and this is m dot within that 1 kiloparsec. So the first thing that I want you to notice is that the gas inflow rate, which is shown here in light blue, is higher than the star formation rate. Okay, so that means that there is some sort of wet inflow, lots of gas supply. And you see that after this period where the gas inflow is higher than the star formation rate, you have this increase in the gas mass. So that's what this blue line is right here. This is the gas mass within 1 kpc. You see this sharp increase in gas mass in the central regions. This is followed a little bit later by a sharp increase in stellar mass, right? So you've brought in all this gas, now you've got tons of star formation happening, and now you've depleted all the gas mass goes down, star formation goes down, and stellar mass is steady within the central 1 kpc. And we see these same trends in all of our galaxies, regardless of...
Yeah, so what about that green line?
Right, okay, getting to it.
Yeah, show me the green line.
Yeah, so the green line is telling you the mass that's come in from a secondary, okay? So these are from mergers. And so, for example, in this case, you see that there was a major merger around the time that compaction happens, right? Whereas in this case, there's a bunch of minor mergers, and here you don't really see anything that significant during compaction.
There's
Okay?
There's a doubling or tripling of the mass from ex situ. It does seem as if, because also the
but it's
example,
significantly...
when there was an ex situ thing, so when there was a merger that happened, be it major or minor, that's when the compaction started.
Yeah, and we do see that happen, again, quite frequently, but sometimes, like in this case, right, this merger, are you talking about this case right here? Mm-hmm. So there's some compaction that happens here, and this compaction seems to happen a little bit before this relatively minor merger,
but that's when it gets into the middle, right?
Yeah, this is when it gets into the middle. Yeah, so maybe. Yeah. But this is certainly, but this is, you know, a mass ratio of less than 1 to 10. So it could be VDI in this case, or it could be mergers, or it could be the combination of the two. As Nir was saying, sometimes a minor merger can trigger instability, and that will trigger inflow to the central regions, for sure. Yeah?
I'm on the same topic. If you could go back one slide.
Sure.
So, you know, I'm not really disagreeing with, in general, what you're saying here, but when you point out the fact that the cyan line is briefly above the star formation rate,
yeah,
as you did. Okay?
Yeah, here. Mm-hmm.
Yeah, or even before that. So, you know, you are putting forward a theory for why compaction happens at that moment. So we would really want to see evidence that the cyan line being above the purple line is really true in every case. And I didn't see it in my quick review of the next page.
Okay, let's take a look.
It really just
Yeah, so here you see that the cyan line is significantly higher than SFR. Here as well, here as well. So they're approximately the same, right? Because you have all this gas inflow in, you form stars, you have outflow.
Okay, well, it wasn't clear to me that you were looking over a much longer period. And I see that if I'm allowed to average over a longer period, I can sort of see what you're talking
Yeah, it's not for a single snapshot, right? You want to sort of just average out at early times. But I agree with you that this is not a huge difference, but it does show you that the gas inflow is supplying enough gas to fuel star formation.
It's important because you're really attributing that to have important physical effects.
Okay, so I'm going to continue, and then we can come back and discuss this more. Sorry.
Do you have also these plots for the outer parts of the galaxy?
Sorry, say that one more time.
Hold the questions until afterwards.
I think you're asking if I have them for every galaxy. Oh. Okay, well,
I'll ask later.
okay. So this is going back to a Guillermo-like plot where we're looking at SSFR as a function of sigma E in this case, not sigma 1.5. And you can see the evolution with little stamps for redshifts, so you can see the time. And if you catch these galaxies, if you observe these galaxies during these times, you would call them a blue nugget. Now, the other half of our simulation sample, so this is representative of about half of the 30 galaxies. Now, the other half do not compactify to such high sigma. So they actually only reach sigmas of about 10 to the 9 or a little bit less. But what I want to point out is that they have a similar evolution. So they compactify and they quench. They might not compactify to as high of a sigma, but it's not that you have two extremely different populations. It's a spectrum between the most compact ones to the least compact ones. So what do these look like? These are mosaics made by NIR. This is gas and stars in the bottom row. And what you see from these different snapshots, this is right before this galaxy really compactifies. You see lots of gas action here, wet inflow. Here, this is the blue nugget stage where we have this very compact gas-fueled star formation here. After the blue nugget is formed, we often see a period where the disk becomes incredibly unstable, and that's what you see here. And in this particular galaxy, you form a red nugget, but you also form this star-forming ring around the red nugget. This doesn't happen in all of our cases, but it happens in a handful of them where you're left with an incredibly quenched central region, but a star-forming outer ring. Okay, so this is for most of the galaxies in our sample, and what you're looking at here is log sigma max versus the time at which compaction starts and ends. Okay, so this is that point where the galaxy turns around, right? It's reached maximum compaction, now it starts to quench. That's this axis right here. And here you're seeing when did the compaction actually start. And what this is telling us, although there's lots of scatter, is that in general, galaxies that reach higher sigma tend to do so at higher redshift and compactify much quicker. We also see a trend with average SSFR before compaction. So what do I mean before compaction? Just to show you, this is max sigma, and before compaction is an average of the specific star formation rate before this galaxy has really become a nugget. So let's go back to this figure, SSFR versus max E. Max sigma, sorry. And what you see is that galaxies which reach that really high sigma, that become really compact, do so by having very high specific star formation early on, okay? And the ones which are less compact do so not only more slowly, like I showed in the previous figure, but also with a lower average SSFR. And this implies that there may be two separate modes of evolution here. The first may be a fast mode, as Guillermo was discussing, which is you have a high sigma gas, which drives a lot of inflow to the center. You have a starburst, which consumes all of the gas in the central regions, and so you quench rather fastly, rather quickly. The slow mode, you're doing it at a lower SSFR, okay? So it's taking you more time to use up all of the gas for star formation. During this time, the halo mass is growing more and more, and your bulge and your quenching is actually a hot halo mode quenching. We also find, if you look at the spin parameter for cold gas in the disk as a function of sigma E, we find this anticorrelation where the galaxies which compactify to very high sigma are the galaxies which have a very low spin parameter. And I don't have time to discuss it in detail, but this is something that was predicted by Avishai and Andy in their 2014 paper on blue nugget formation, that galaxies with low spin, where our disk is obviously low, that's where you expect to form compact galaxies. So to summarize, we see a very characteristic sequence of events in all of our simulations. We see a dissipative compaction that's fueled by both mergers and VDI. This leads to compact star-forming galaxies. Some of them are incredibly compact and high sigma, so these are the blue nuggets. Some are less so. And then we see fast quenching to compact ellipticals, the so-called red nuggets, and perhaps evidence for slow quenching to diffuse ellipticals. Thank you.
Questions for Andy? Yes.
I was just curious, when
Yeah.
you were talking about it earlier, what is the rest of the galaxy doing? Put another way, is compactification driving up the central surface density, or is it decreasing the half-mass radius? So for the galaxies which become highly compact, okay, in those cases, RE is always staying at about 1 kpc. Okay, so it's actually just driving a lot of mass towards the central regions. In the galaxies which don't become very... Can I just say, if RE stays the same, then presumably, and it stays at 1 kpc, then what's happening within 1 kpc is being mirrored by what's happening outside of 1 kpc. Otherwise, it wouldn't keep the same half-mass radius.
Yeah.
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 And I'm just trying to get my head around this word compactification. Is it an increase of stellar density, or is it a decrease of half-life mass?
Yeah, it's both. I mean, it depends.
But I heard that the half-life radius stays the same.
They say, there is a change in half-life radius. For example, if there's a major merger, you do see spikes in changes in RE. But in general, during these periods of compactification, you see that RE stays approximately the same and at about 1 kpc. So you're driving in a lot of mass to the central regions. Sometimes RE decreases by a little bit, but...
I just don't understand.
There's no complication.
What?
If RE stays the same, there's no complication.
Right. What does compactification mean?
It means that you've centralized your mass.
But centralized your mass, AD, surely means the half-mass radius changes.
No,
But-
remember what's being positive sigma. Sigma's going way up.
This is what I'm trying to understand.
But that's what compactification means in
So
practice.
to answer my question, compactification means an increase in central density
Yes.
that is apparently matched by an increase in mass outside of a kpc, because the half-life radius doesn't change. The half-mass radius doesn't change.
Approximately, yeah. It's...
But generally, they're not shrinking.
No,
they're not shrinking by very much.
What must be changing is the half and the radius of the star forming gas.
Right.
So the star forming gas is a smaller half life radius, but the half life radius of the total gas doesn't change much.
Yeah, total mass. Yeah.
Let me clarify one thing that he said 3 times. The gas is driving the combustion. Okay? This is not something you see in RE. Okay? This is the physical process. You ask about the stellar distribution. The stellar distribution, as you showed, is following the stars in many ways. Once because the gas that compactifies makes new stars. Also because stars from outside sound frequent, but not as much. So what you do see is a later compaction in the stellar distribution, which means that RE also shrinks, but a little later in most cases. Okay? Some stars are left out. To some extent it is, to some extent it's spheroid, is left out. But in some way, RE does follow the first compaction.
Okay, I think we need to move on to our next speaker.